Hi there everyone. So today I would like to show you some relation between energy and momentum. So we're gonna look into impulse, force time graphs and such. Now let's recap our Newton's second law of motion. So what does Newton's second law state? Force equals mass times acceleration. So let's take a different look at this. For example, is there any other way I can express acceleration in terms of a change of velocity? Well, acceleration is a change of velocity over time. You could even argue that it's a change of velocity over a change of time. Now, if you consider that you start counting at the beginning, which would be your time equals 0, then this delta t, change in time, would just be time. And also, what is your change of velocity? If we're taking into consideration the notation that we have been using so far, in which u is the initial velocity and v is the final velocity, then we would have v minus u. And we can, in principle, apply this to Newton's second law. And what do we get? Well, F equals m times v minus u over t. So what is mv and mu? Well, if u is the initial velocity, mu would be the initial momentum. And mv would be the final momentum. So this here, if we expand, we don't need to, but if we expand, take a look. This is the final momentum minus the initial momentum. So this is in fact a change of momentum over time. And again, if you're not really counting time here, just counting a change of time, you can keep this change. It's okay. So force can be described as a change of momentum over a change of time. If we rearrange this relation here, we could then write that the change of momentum is the product of the force and the change in time. So this product of force and change in time is what we call impulse. The units that make more sense here are Newton's seconds, right? Newton's second, because force is measured in newtons and time in seconds. So impulse, usually the units are Newton second. Now it's important to notice that Newton second is the equivalent unit of kilogram mass second to the negative meters second to the negative 1. Right? So those things, they mean the same thing. So if you get, for example, your definition, we have done this in the past, but if you get your definition of force equals mass times acceleration and you replace here and you work it out, you should find exactly the same thing here. So let's take a look at one example here. A mass of 0.48 kilograms of water leaves a garden hose every second. The nozzle of the hose has a cross-sectional area of 8.4 times 10 to the negative 5 meters squared. The water flows in the hose at a speed of 0.71 meters per second. The density of the water is 1,000 kilograms per cubic meter. Calculate A, the speed at which water leaves the hose, and B, the force on the hose. So, if 0.48 kilograms of water is flowing per second, that would mean a volume of 0.48 over 1,000, oops, too many zeros, 1,000 cubic meters, leaving the hose per second. So this is basically per time. So this is volume per time. Now, what is another way of looking at volume per time? Well, volume is an area times a height or a length over time. What is a length multiplied by time? That's speed. So that value is also the area of the cross-sectional area of our hose times the velocity. So if we rearrange this, we would get that our velocity is 0.48, which is our volume here per time over 1,000. Right? I've just rearranged this equation here. So we divide by area there. So there will be a multiplication here by area. So our area was 8.4 times 10 to the negative 5. Now I am omitting all the units because everything is in meters, seconds, kilograms. So everything is in SI units. So I don't have to worry about them. I can just calculate the values, and afterwards I'll know that my velocity here will be in meters per second. So if I work those values out, I should find 5.71 meters per second. And again, we've got too many significant figures, so we should round this to 5.7 meters per second. Now, letter B asks us for the force on the hose. And for that, we will have to use that the force on the hose will be the change of momentum over change in time. So this can be visualized as mass times the change in velocity over change in time. So we do know in this case what is our mass over time. How is mass changing with time? This we also call flow rates or mass rates. So it's telling you how much matter is coming out of the hose at a certain time. So how many kilograms per second, for example, which is exactly what we have, 0.48 kilograms per second. And what would be our change in velocity? Well, since it's going from this speed, which is 0.71, up to 5.71 or 5.7, so we can visualize that the change in velocity here is 5 meters per second. So we can just multiply 0.48 kilograms per second by 5 meters per second. Since everything is in SI units, my force here will be in newtons, and the result should be 2.4 newtons. So, another example here. An impulse of 85 newton seconds acts on a body of mass 5 kilograms that is initially at rest. Calculate the distance moved by the body in 2 seconds after the impulse has been delivered. Well, we have to remember here that impulse means force multiplied by a change in time. We can look at the units here, they tell us something, and you should have those equations in your physics data booklet. So the value here is simply 85. Now, we know that the time elapsed is 2 seconds. So we should be able to find the force. But we're looking for the distance. Now the whole point here is, this is also the change of momentum, which is mass times change in velocity. We know that the initial velocity is 0. And the mass is 5 kilograms. So the change in velocity would then be our change in momentum, or our impulse, divided by mass. So our change in impulse, our impulse or change in momentum is 85 newton seconds, and our mass is 5 kilograms. So the change in velocity here is 85 divided by 5, which is 17 meters per second. So if our object was moving at 17 meters per second for 2 seconds, then our displacement will be 17 times 2, which is 34 meters.